So let's review. Simple harmonic motion. And now this is for both mechanics and electromagnetism. First, let's start with pure mathematics. If I have an equation where I say some variable x is a function of some variable t is equal to a constant a times cosine omega t, where omega is some constant. Okay. Well, I'm going to take the derivative of this thing twice. And I get a very interesting result. Well, I mean, you know what a cosine wave is, right? Well, let's take the derivative. So we're going to get dx dt. Now, of course, usually if x represents position, then we've got, dx dt that represents velocity. But x can be anything, and t can be anything, and omega can be anything. All right, let's just think of this as purely abstract mathematics. And so we get negative a omega sine omega t. Is that right? Yeah? The negative goes there? Okay. And then we take the derivative of, again. We get negative a omega squared times the cosine of omega t. So in other words, if you take the derivative of sine, you get cosine, but you got to use the chain rule, and you get the omega out front. And there you go. And so we have this idea that d squared x dt squared is equal to negative omega squared times, well, a cosine omega t is my original function. X is a function of t. You know what? I'm not even going to put that function of t. I'm just going to leave it like that. So look, now this is a differential equation. This is a solution to that differential equation. So if I look at this, and I say, all right, I've got some expression where I've got some function, and that function is equal to its second derivative, or its second derivative is equal to that function, but we got a minus sign out front, and we've got some constant out front. Well, the solution to that is a cosine wave. Or, you can do the same thing with a sine wave, right? If you say x is a function of t is equal to a sine omega t. Well, if you take the first derivative, take the second derivative, okay, and look, once again, we've got a sine omega t. Well, that's just x. So we've got d squared x dt squared is equal to negative omega squared times x. So I have, in other words, I've got two different solutions to this differential equation. Notice I end up with the same differential equation. Right here, right here. Well, it's got more than one possible way of expressing it, either a cosine wave or a sine wave. But really, the cosine wave and a sine wave, they're pretty much the same thing. It's just where they start is a little different. Okay? So, look, any time you can express a function or express a quantity, is either a cosine wave or a sine wave, we call that simple harmonic motion. Okay, so now we've had a couple of different examples. I'm going to go over two examples of this. where, now there's another one, there's pendulums. I'm not going to cover pendulums. But we had a mass spring system. Now this is in mechanics. So here's my mass. I'll put little reels on it. This has a mass M. This has a spring constant K. Remember what the spring constant represents. It's how much force you need to stretch or compress the spring 1 meter. It's newtons per meter. Okay? Now, of course, a lot of springs, you can't stretch them a full meter, but that's okay. It's a ratio. So, you might be only able to stretch it a centimeter or 0.01 meters, but that's okay. How much force do you need, per meter to stretch or compress the spring? Now, we have Hooke's law that says, all right, the force on this mass is going to be equal to negative kx. Okay, well, what is negative kx? That means that if I start here, here's the equilibrium position, so x is 0. If I stretch it out, this far, the force acting on here, if I pull this out and then release it, the force acting is to the left, the direction of the force is to the left, even though the displacement was to the right. Now, if I compress it, if I push it in over, put the crate over here, the displacement is to the left, or negative, but the force is positive. In other words, the direction of the force is opposite to the direction of the displacement of the object from its equilibrium position. Okay? That's what that negative sign means. Well, if I look at this and I release it, once I release it, if I draw a free body diagram, well, I got gravity and I got like a normal force, and they're just canceling each other out. The only force acting is the force of that spring. So the force of the spring is a net force. It's the only force acting. So I can say this is equal to MA. So MA equals negative kx. Okay, well, what if I divide both sides by m? I get an expression for acceleration. The acceleration equals negative k over m times x. But what is acceleration? It's the second derivative of position. Acceleration is d squared x over dt squared equals negative k over m times x. Now, this is a differential equation applied to the position of a mass spring system. So in other words, if I release this, it's going to oscillate back and forth, and if I trace its position as a function of time, I'm going to get a sine or a cosine wave, depending on where I start. Okay? So, but it also tells me more than that. If it also, this right here, that's omega squared. That's the angular frequency. Okay, this tells me how many radians per second I'm going through. So omega is equal to the square root of k over m. Now, one thing you can do is look at the units for this, just to check out what the units should be, right? What's K? That's newtons per meter. What is the units for M? Kilograms. It's mass. Okay. So now we can go through this. This is a kilogram meter squared per second squared.
Oh, thanks, Lee.
What?
I just asked what a newton was, and you just answered my question.
Oh, no. Kilogram meter per second squared. That's a joule right there. Kilogram meter per second squared. Divided by a meter divided by a kilogram. So the kilogram cancels the kilogram, the meter cancels the meter. I have the square root of 1 over seconds, which we cleverly call per seconds. Or we can insert that phantom unit, radians per second. Okay, there. And so this really, right, okay. So this is what we did with a mass spring system. Okay, we got a situation where one quantity, the second derivative of a quantity was equal to the original quantity, but in the opposite direction times some constant out front. Okay, well today when we talked about LC circuits, probably should get the book out. All right, well, what we did was we had a fully charged capacitor. Am I still on screen? Yes. A fully charged capacitor with an inductor. Okay, now when it's fully charged, we said that the energy stored on that capacitor, well, the total energy on here is equal to, well, once I close it, this is going to cause a current to flow, but that current establishes a magnetic field in here, which pours energy out of the capacitor into the inductor. Then as the current tries to collapse, you know, if you have zero current, you've got no magnetic field in here anymore. So the energy has to be somewhere. Well, as the current tries to collapse, the energy in the magnetic field keeps the current going until all the charge is now on the positive side, and this is all negative up here. And then it does it over and over and over again. And so we said, well, at any given time t, the energy in here, which is Q squared over 2C, that's the energy of a capacitor, plus the energy in the inductor, which we had was 1/2 Li squared. We derived that. So now if you don't remember that, you got to look them up. Okay. Well, these two together have to add up to the total energy we started with, which was, depending on where you want to start. You want to start where all the energy is on the capacitor, you could do that. Or you could start where there's no charge on the capacitor and you've got maximum current, so all the energy is in the inductor. You could do that. Doesn't matter where you start, because what we're going to do is we're going to take the time derivative of this. Now, when we do that, well, this is a constant. The total energy in an LC circuit is constant. Remember, the only way for energy to exit a circuit is through some kind of resistor, at least right now, in terms of what we've taught so far. So that resistor, there is no resistor in here. This is a pretend, superconductor of some kind, all right? Now, you take the derivative of this, you get 0, because this is a constant with time. And then we get 2q dq dt, right? That's the derivative of this over 2c, right? So that'll cancel. Plus, well, what's varying here is you have 1/2 L, then you have 2I di dt. That's what happens when you operate the derivative on this guy. Now, one thing when you're going to do that, you got to really make sure you know what's varying with time. So when you take the time derivative, you get something, and what's a constant. So it just stays out front. 2, so far in the history of the world, 2 doesn't change with time. Now, our capacitors are not.
Large values of 2.
Yes, they're very huge. Never mind. All right, so this is a capacitor here. We're going to say it's fixed. The inductor is fixed. We're not going to let it change with time. And so the only thing that's going to change with time is the charge on the capacitor, which is Q, and the current running through the inductor, which is I. Those change with time. And so now we've got Q over C times dq dt will be equal to, let me just put that other stuff on the other side. Well, the 2 cancels the 2. That's going to be equal to negative, right, L I di dt. Now, if you look at what is dq dt? That's the current. So what happens is that this cancels out. So what I'm going to do is divide both sides now by L. So that'll cancel that. Negative L, so I'll put the negative on the other side. So what I'm trying to do is solve for di dt is equal to negative 1 over LC times Q. Huh?
Okay, I have a question. Is there any specific reason why it's not just negative Q over LC? It's 1 over LC times Q.
Where do you get the 2?
Okay, no, negative Q, not negative Q. So negative Q as in queen. As
Oh. Well, what am I trying to do?
I don't know.
Why am I putting it in this? Look, do you agree with me that it can be in any order you want? I mean, you can arrange this mess algebraically any way you want, but I'm choosing to do it this way because I'm the teacher. I
was wondering, like, is there like a particular reason why?
Yes. You want to know why?
Please don't say because I said so.
No. I'll show you why.
Okay.
Boom. I'm trying to get to here, to simple harmonic motion. Now, look.
Got it.
Now what? Quiet, please. Shh. I am recording this, so be quiet. Now this is I, right? This is current. What is current? Current is dq dt. So what is this right here? It's d squared q dt squared is equal to negative 1 over LC times Q. And folks, that is simple harmonic motion. Well, simple harmonic motion of what? Well, what it is it's a simple harmonic oscillator. I really should call it an oscillator because what is oscillating here in the form of a sine wave or a cosine wave is the charge on the capacitor. The charge on the capacitor, if I was to graph the charge on the capacitor as a function of time, I could do it with a cosine wave. In other words, if I said Q as a function of time, it's going to be equal to some amplitude, well, which is the maximum charge. We'll just call that Q max, which would have to be given, times the cosine of, now what is omega, here? Well, in simple harmonic motion, what is this constant equal to?
Omega squared.
Yeah, omega squared. So omega squared is equal to 1 over L times C. All right? Leave them alone. All right. Now, so if this is omega t, this is the square root of 1 over LC times t. And so this it'll look something like this, right? If this is cosine, it'll look something like this. So this is the charge on the capacitor, and this is time. Well, how much time? Well, we can figure out the period, right? What is the period? The period is equal to 2 pi over the angular frequency. That's the time to complete one oscillation. And this is what I didn't have time to do today in class because the stinking bell rang. Okay, so look, so this is going to be 2 pi divided by the square root of 1 over LC. Now, let me ask you this. What units does LC have? 1 over LC have to have? Yeah, you can. Omega squared. Per seconds squared.
But when you square root.
And when you take square root, right. It has to be omega. This has to be per seconds, because when you 2 pi times a per second is or divided by a per second is a second. All right, now this all works. But in any case, what I really want to get to with this review is this. Let me get that. Is that any time, look here, I had a mass spring system, and we ended up with the second derivative being equal to the original function, but a negative with a constant out in front. What's the solution to that? A cosine wave or a sine wave is a solution. Now, when I did an LC circuit, I got the same mathematical structure. I got the same kind of differential equation, which means the solution to it is a sine wave or a cosine wave. Now, with the mass spring system, you're talking about the position as a function of time. Here, we're talking about charge on the capacitor as a function of time. But the idea is this. It's going to oscillate. It's going to oscillate the same way. So, I have seen a really clever problem where you end up, at the end of the problem, when you evaluate the equations, you end up with this mathematical structure. And they tested to see if you recognize that as simple harmonic motion. So keep an eye on it. It's very common in nature. I mean, simple harmonic motion is something that comes up. Okay, and and it's kind of cool. All right, that is it.